Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. Right now we're in section 214. So we just talked about intersections and unions and how they're kind of like ignoring operations. Now let's get back to what we wanted to do. We take a power set and we want to look at merges on that power set that preserve certain types of structure. And we're doing this in order to develop a model that we can use to study logic. Now we've discussed how it can preserve, we've discussed what it means for merges to preserve the partial order structure of the post set, with arrows being inclusion or subset of. But also we want to now look at merges on those power sets that preserve operations such as intersections and unions. So the last little subsection helped us kind of build up to this. Now here we go. Let's look at a certain type of a merge with, and we're gonna be looking at the subsets, which are elements of the power set. But the subsets could be just thought of as code or strings of ones and zeros. So, for instance, let's take a subset in our power set and think of it as code with these zeros and ones. And let's look at a merge, and that has the following idea, meaning that it ignores certain positions. So the codomain is of this merge is simply strings that have red blocks in certain positions, and everything else will look the exact same as its pre-image where it came from. So thinking about that, I mean, you think, what's the fiber of this codomain element right here with a red block here, red block here, red block here, and then 1, 1, 1, 0, 1, 0, 0. Well, precisely anything that has 0, 0 in this position, 1, 0, 1 in that, and over here, and 1, 1 here. And these red blocks could have had anything at all in the pre-image, and kind of the intermix of that. Well, there's two different options for that there. And for here and here, so 2 times 2 times 2, that's 8. The pre-image of this one codomain element in this particular merge would be 8. There's 8 different codes that would get us that exact same thing. And here's another example. What would this turn out to be? Notice you have a 1. Let's see, we're blocking out that position, but then 1, 1, 0, and we have a 1, 1, 0 here. 1, 0 up front, 1, 0 there. So basically, we're just blocking out certain positions entirely. Let's see. So here's an example of 2 different subsets that are in the exact same fiber of this merge, meaning they have the same image. They have the exact same image in this merge. Okay, so we're going to describe such a merge like putting different things together, like taking different things in your different subsets and kind of declaring that they go to the same place in a via surjective function. We're going to call this type of thing set up this way to kind of figure out what our fibers are in this particular way by blocking out a block out merge. Okay, so here's the question. If you have a block out merge, so a merge that's kind of has this block out type structure, does it preserve the operations union and intersection? We've already talked about how intersection and union are kind of like ignoring operations, just like a block out merge is like an ignoring function type thing. Do those coincide and work together? The answer will be yes. Let's take a look at the particulars. So let's suppose we have a merge, and we'll call it this. All right, we start at the power set, and we're going to go to P. Why did we use this letter P? So this is a script P to mean power set, and this is another type of P. That's to mean partition, because when we're merging, really basically what we're doing is we're chunking, and the codomain is just the chunks, you could say. So in the codomain then, so after we've chunked, so we take two chunks together and we intersect, well, kind of like the image via the merge of intersection. Okay, hopefully we have an operation like that. Is there an operation like that? Basically, is there an operation on the codomain that makes this diagram commute? Meaning we can apply intersection before the merge, or we do the merge and then we perform this other intersection on the chunks, and do we arrive at the same place? Okay, so that's the idea. What does that mean? This just means that we're applying the merge to both parts. Like if we have two subsets right here that we want to take an intersection of, well, why don't we find the chunk that this guy's in, the chunk that guy's in, and that's kind of what this is. And we take those two chunks and we're supposed to apply some operation on them in the codomain and get something out. And that something should correspond to the same thing that that would be done if we did it before. Okay, so we'll keep going with this and see how this is going to work. So to see if this actually works, well, let's just think about what this intersection on the codomain should be. So let's just take two chunks up here, and we're going to work our way around. Take the pre-image of those two chunks. So we're going to get a plethora of subsets over here and subsets over here. And no matter which subsets we take, let's see, we intersect them and we're going to get different options over here. So we have a number of different subsets we have over here. But no matter what that is, do they all go to the exact same chunk? Do they live in the same chunk? And if they do, then we know this operation is well defined. So that's kind of the idea that we want to use, okay? And that also described it. So let's see how that would work. So let's start with two chunks and see if we can, if there's a well-defined way of kind of intersecting them in the codomain so that this works. So it's a well-defined transfer that the merge actually preserves that operation. Okay. So, well, okay, so take pre-images elements. Okay, that's the map. All right. So, when it says little boxes, that's just referring to what happens in this original domain right here in as we take a pre-image over here. So just a fiber of this map, if you will, if you take two chunks, what do we get over here? That's what that's referring to. So here's here is a specific example. Okay, here's an example. I've taken something in P cross P. So this is an element of the codomain, right? Because it has some red blocks. This is another element of the codomain. And let's take the pre-image of that. What is it? What is it? Elements in this pre-image are obtained by replacing this with anything. Okay, so this is one member of the box. In fact, let's just represent the whole pre-image of both of those, of this pair of codomain elements as this. So instead of box, we'll just write anything, 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 anything. So this is like, this represents all the different options for things that could be, for different subsets that you could be wanting to intersect that would actually have, would have this ordered pair as its as its image via the merge. Okay, so let's see what happens. Where are we going to send those elements? So let's go back to this diagram. So right now we're right here. So we took a pair in P cross P, and we sent it back to a lot of things, which we'll call a small box here, in power set cross power set, which is right here. Okay, power set cross power set. So we got something here and we took it to here. Next, so we have a lot of different things. Now we're going to take it down here and take intersections of each of those pairs, and then we'll get a number of subsets down here. Let's see what that'll be like. So we're here. Now we're going to take intersections of these guys and see what happens, all right? Okay, so we're going to think about this as being the first subset and this as being the second one. So basically in this one, we circle anything that has a 1, okay? Now we don't know if we're going to circle the thing in here in this red or here or here. Remember, that's how our intersection went. We took our first subset, we circled all the ones. We don't know if there's ones in here to circle, but so we don't know what's going to happen. So in our result, we'll just say something, something, something in those particular positions because we really don't know. But that's okay. We'll just keep it as something for now, and we'll see if maybe eventually won't matter what it was. Okay, so, but in the positions that we do know, then we cancel out what's outside of those and we just take that right there. Okay, and we get something, and we just focused on what was outside of it instead of of the red area, and we just kind of said, well, we don't know what's happening in the red, but we'll just say it's something. So that's what's happening to all the elements in the pre-image over here. Okay, so this is what all the subsets are going to look like. Okay, they're all going to be of this particular form. When we get down to when we've taken intersections, they're all going to look like that with the somethings in there. So this is where we're at. All subsets that have taken us down here look like that. Now we just have to see if now when we merge, is this going to go to one element? And it actually does. The something didn't matter, and it went to the exact same thing over here, which tells us that we have a well-defined operation that makes the commutative diagram work, or so the merge actually preserves that operation of intersection. So, and in particular, that's because intersection itself was an ignoring operation in this case, and it kind of followed well with what was happening here. And the thing that happened in the anything, I mean, it didn't really get out of it. What was in the red stayed in the red and didn't come out, and vice versa. So we were pretty good because of that. Union is a similar type of idea, and blocking off actually also preserves unions likewise. So what we have is blocking off preserves both intersection and union. It's kind of a neat idea. So any blockout map will preserve those two operations. Thank you for watching.